Okay, good morning everyone. Let us take up where we actually take up the story where we left it yesterday morning. And I think yesterday afternoon you started using the program. There were a lot of queries, a lot of questions in your mind as to, hey, why does the stress path look like that? Why does the stress strain curve? There must have been a lot. And indeed, these are the questions that were asked in the assignment. So I thought maybe I'll just discuss some of that with you, so that it eases your way through the assignment, so that you don't have to crack your head over the thing, it kind of, yeah. So, okay, so let's start with let's start where we stopped yesterday. Then we stopped where the Mohr-Coulomb, where we start talking about the angle of dilation of the Mohr-Coulomb. And just to recap some of the things I said yesterday, and I said that Mohr-Coulomb will always predict dilation if the angle of dilation is greater than 0, okay? But real soil can either compress or dilate. The thing is about Mohr-Coulomb is that it cannot predict compression. That means to say, if you shear the soil and if the soil skeleton try to compress in the process of shearing, you cannot predict it with Mohr-Coulomb. And that's why you cannot generate positive excess pore pressure with Mohr-Coulomb. That's the problem with the Mohr-Coulomb model. You can only get up to an A value, a Skempton's pore pressure parameter of 1/3, no more than that. Okay, you can get less than 1/3 if you specify an angle of dilation greater than 0, but it will keep going non-stop. Okay, so if you specify an angle of dilation that is greater than 0, you find that the soil will continuously try to dilate. Okay, and so when you subject it to prolonged shearing, the volumetric change becomes very unrealistic. And so that is because the Mohr-Coulomb model does not have a mechanism by which it can terminate the dilation. Okay, and then I define the generalized shear strain for you, the definition of the generalized shear strain, and it's really quite a big chunk of terms, and I won't bother to read it, but essentially you can just regard it as some way of measuring shear strain, okay, by putting in different shear strain components into the basket and giving them different weightage. That comes out with a certain number that you call generalized shear strain. So this is the definition, the formal definition of the generalized shear strain. And it turns out that if you adapt it to triaxial condition, alright, the triaxial condition is very straightforward because you have let me just sketch this thing on the board. The triaxial condition essentially says that gamma xy, gamma yz, and gamma zx equals to 0. They are all 0. So the last part of the thing totally disappeared. Alright? And if we use the axis x, y, and z, then obviously sigma x and sigma z must be the same. Agree? Okay? Sigma x equals to sigma z. And so as a result, what happens is that this guy disappeared as well. And these two are essentially the same because this is sigma x minus sigma y. This is sigma y minus sigma z, but sigma z is equal to sigma x. So basically this is just the negative of this, but when you square the negative sign goes out of the equation. So the square is exactly the same. Okay, so this is exactly equals to 2. This thing added together, alright, is exactly equals to 2/3 square root of half of sigma x, epsilon x, epsilon x, not sigma x. Epsilon x minus epsilon y. Okay, 2. There's a 2 here as well because you added up twice. This should be epsilon. Okay. So when you work that out straight away, the 2 cancels out, and when you take the square root of that, it's just simply epsilon x minus epsilon y or epsilon y minus epsilon x. Basically, it comes out as a positive number. Alright? And so essentially, you get 2/3 of that. That's how it looks like. Now, on top of that, supposing this is epsilon y. Alright? That is epsilon x. Okay? If you have an undrained condition, it turns out that in an undrained condition, okay, epsilon z equals to epsilon x equals to half, minus half of epsilon y. Alright? Because there is a condition that the volumetric strain is equal to 0 in the undrained condition. So if the volumetric strain equals to 0, we know epsilon x plus epsilon y plus epsilon z equals to 0. That is the volumetric strain. And epsilon z equals to epsilon x. Alright, so now we can change this to 2 epsilon x plus epsilon y equals to 0, which says epsilon x equals to minus half of epsilon y. So this is how it looks like. So when we substitute this back into the 2/3, the equation with the 2/3, immediately it turns out that epsilon s, which is the generalized shear strain, is actually equals to epsilon y in undrained triaxial condition. That is the axial strain. So in undrained triaxial condition, this reduces very nicely to the axial strain. Okay. Now, then how does the angle of dilation feature into the plastic deformation? And the plastic deformation comes into the picture. It turns out that the angle of dilation is a parameter that relates the volumetric plastic strain increment, the incremental plastic volumetric strain, to the incremental plastic shear strain. That is to relate this change in plastic volumetric strain to the change in the plastic shear strain. And that relation basically is a function of the angle of dilation. So now let us take a look at this. If the angle of dilation is 0, then obviously this thing reduces to 0. Alright? Because the right hand side reduces to 0. If the angle of dilation is positive, and the angle of dilation cannot be negative. Usually when you try to put an angle of dilation, a negative angle of dilation into a software, it will reject you. It will tend to reject you. So it can only be positive. And so if it is positive, what happens is that this whole thing will then be negative. This group of terms will be negative. Alright? It will be negative. And as a result, what happens is that if your plastic volumetric strain, a plastic shear strain is increasing, then in fact your plastic volumetric strain is negative. The increment is negative, which means it is decreasing. Now what does that mean? That means the sample is actually dilating, because negative volumetric strain increments means dilation is dilation. You know, our convention is compression is positive, dilation is negative. So this goes negative, so it implies dilation. And so this is how it controls the dilation. This is how it controls the dilation. Okay. Now, I won't go into the definition of the generalized shear strain, because it is again based on the idea that the deviator stress multiplied by the generalized shear strain is a proper measure of the energy of distortion. This is how it worked out. Okay. But we do not need to go into the detail. There's only one thing I need to highlight to you, which I think is important in your future coursework and also in your future practice. And that is that the generalized shear strain is actually directly proportional to the deviator stress. And that constant of proportionality is 1 over 3 times the shear modulus. It is not 1 over the shear modulus, it's 1 over 3 times the shear modulus, so Q over 3G. Alright, so this is an important point. Okay, so if you have an elastic material and you know the deviator stress, then you can find the generalized shear strain. If you have a non-linear material and you know what is the this is for an elastic material, okay, so for a non-linear material this will not apply for elastoplastic material, but for an elastic material, linear elastic material, this is applicable. So that if you know what is the deviator stress, you want to find what is the generalized shear strain, this is the way to find it. Very straightforward. Okay, just divide it by 3 times the shear modulus. Okay, the next thing I want to talk about is the idea of associated flow. Now, in plasticity, you very often come across two terminology in terms of the flow rule. One is associated flow and one is non-associated flow. I think yesterday in the program, some of you came across, one is NAF, meaning non-associated flow. The other one is associated flow. Okay, so in the next part here, I want to say a little bit about what is associated flow and what is non-associated flow. Both of these are essentially assumptions only. So If you ask me to prove it, I can't prove it. In fact, it's all assumption. All right, and the idea of associated flow is an assumption which says, or hypothesis which says, that the plastic potential is completely coincident with the U locus. Completely coincident. So if you take the Mohr-Coulomb model, the U locus is the Mohr-Coulomb failure envelope of the Mohr-Coulomb U locus. Correct? And it's a straight line in this direction. So what we do is, we say, this is also the plastic potential. This is what we mean by associated flow. Alright? Associated flow. Now, what is the consequence of this? How do we apply this? It provides a very simple vehicle for us to examine how plastic flow occurs, how the flow rule directs the plastic flow. Okay, so you have a material that you start loading from here, and this is the initial stress path. It's vertical because it's elastic. Alright, and once you get to here, the black arrow represents the strain increment vector. It's not the stress path anymore, because the stress path cannot jump out of this thing. At the most, the stress path can go along this, but it cannot exceed this. This is out of bound. This whole area is out of bound. Alright, so basically, once the stress point reaches here, okay, then you start to look at the strain increment vector. Now, how does the plastic potential in this particular case, this special case, guide the strain increment vector? And the way it guides it is very simple. The plastic potential is also equal to the U locus. Also equal to the U locus. So basically, this is the plastic potential. So at this point, if I want to assess what is the strain increment vector, the strain increment vector must be a vector that is at right angle to this particular line at this point. Alright. So basically, here you can see the strain increment vector now is pointing in this direction. Now, if the strain increment vector is pointing in this direction, how does that determine the flow? How do you interpret this strain increment vector? The way you interpret the strain increment vector is this. Unfortunately, I haven't got it there, so I will just sketch it on the board. So you got a strain increment vector. This is the plastic potential, and this is the strain increment vector at this particular point. The strain increment vector at this particular point. This is Q, this is P dash, and this is the delta epsilon Vp, delta epsilon Sp. Alright, this is the strain increment vector. Now, what does the strain increment vector tells you? Actually, the size of the strain increment vector is not important. It is the direction of the strain increment vector. Alright, and the direction of the strain increment vector must be interpreted as this. It has two components, a vertical component and a horizontal component. Correct or not? Okay, let's say the gradient of this strain increment vector is n, for instance. For instance, is n. Alright, is n. Then this component represents the plastic shear strain component, and this component represents the plastic volumetric strain component. Because this component is aligned in the vertical direction, that component is aligned in the horizontal direction. It's the negative horizontal direction in this case. Alright. So on the other hand, if you have, okay, so now how do we look at this? Very simple. All we need to say is this. This divided by this, let's call it eta. Okay. This thing divided by this thing. Alright. This thing divided by this thing. Delta epsilon Sp divided by delta epsilon Vp is equals to minus eta. That is the gradient of the thing. Alright. So this direction, or rather the gradient of the strain increment vector. The gradient of the strain increment vector in this case is negative eta. Basically tells you the ratio between the plastic shear strain increment and the plastic volumetric strain increment. You follow? Okay. So this is how the plastic potential guides the strain increment vector, and how it actually specifies, all that it specifies is the ratio of the two components, the plastic shear strain increment and the plastic volumetric strain increment, the ratio between the two components. That's all it specifies. So the next question is, of course, how do you use that? How do you use that to determine, how does the program use that to determine how that material is going to deform. That is the next important question. So basically, for an associated flow rule, if you look at that, on the U surface, what is the gradient? The gradient is M, correct? M, alright? 6 sine phi dash over 3 minus sine phi dash. Let us go back to revise ourselves. Where does this M come from? You can see this is the M, and basically we are saying that when you transform the Mohr-Coulomb failure envelope to PQ space, you get an equation of the form Q equals to MP prime plus C, where M is the gradient of the line. Alright, and M in this case is 6 sine phi dash over 3 minus sine phi dash. Is that okay? Alright, so that is how the M comes into the picture. So when you draw a line, say this is the U locus, then the gradient of this is M. Typically, in a triaxial condition, is M. Clear? Okay. So, if you take this to be M, okay, then obviously on the U locus and on the plastic potential, they are one and the same thing. Delta Q over delta P dash is equals to M. Now, the associated flow says that the strain increment vector is perpendicular to the plastic potential, which is in fact the U locus. Okay, and in Cartesian geometry, we all know that if you got two lines perpendicular to each other, there is a condition that says that the multiple of the gradient, the product of their gradient is equals to -1. Remember that? Cartesian geometry. Alright, I can't prove it. I don't know. I can't remember. I think it's quite easy to prove, but I won't bother to prove it here. I think I kind of ask you to accept it. If you can't, you kind of forget it. But look up your secondary school textbook. It's probably there. So anyway, the product of the gradients, the slopes of the two lines has to be -1. So so basically the gradient of this is equals to delta epsilon SP over delta epsilon VP. Correct? Alright. The gradient of this line is delta Q over delta P. Agree? So we can immediately write that the gradient of this multiplied by the gradient of that equals to -1. Correct? Okay. And immediately, because this is equals to M. Delta Q over delta P dash equals to M. You see that? Alright. Because this is equals to M, this immediately leads us to realize that delta epsilon VP, the plastic volumetric strain increment, is minus M times the plastic shear strain increment. Minus M times the plastic shear strain increment. Is that okay? Alright? Okay? So, basically, what it means is this. If you have an associated flow rule on a Mohr-Coulomb, which is usually not used in practice, alright? So, if you use GeoFEA, please don't turn on the associated flow. It's not realistic. It's unrealistic. And I'll tell you why it's unrealistic. Okay. If you have a drain test, your plastic volumetric expansion will continue because at the rate equals to this, given by this. Alright? So, for every unit of increase in plastic shear strain, the plastic volumetric strain will increase by minus M times that unit. Is that alright? Okay? So, that means the volume will keep on dilating. Okay? So, this is a contradiction to real soil behavior. Now, let us pause for a moment to examine what this means in terms of the angle of dilation. On this equation, we have noted that for associated flow rule, delta epsilon VP, the plastic volumetric strain increment, is minus M times the plastic shear strain increment. In our general definition for the angle of dilation over here, we have said that the plastic volumetric strain increment is minus this times this. Alright, so now let us compare this and see what is the implication of this thing. The implication of this is as follows. Let's examine this thing. Delta epsilon VP equals to minus M delta epsilon SP. That is the equation on the other slide for associated flow. And what is M? M is 6 sine phi dash over 3 minus sine phi dash. Agree? So it's minus 6 sine phi dash over 3 minus sine phi dash multiplied by delta epsilon SP. Agree? Okay, now if you compare these two equations, this fella and this fella, you realize that actually the angle of dilation here, I don't know how to read this term. Somebody tell me how to read. Xi, right? Xi. Xi will be equals to phi. It automatically implies. So therefore, unfortunately the program doesn't use xi, it uses delta, I think. Yeah. Therefore, in the special case where you have assumed associated flow, that is equivalent to assuming an angle of dilation that is equal to the angle of friction. And that is usually regarded to be too high, far too high. It prescribes too much dilation. Is that alright? Clear? Okay. So the associated flow is nothing more than the special case of a non-associated flow in which the angle of dilation is equal to the angle of friction. And in principle, if you set the angle of dilation equals to the angle of friction, and you run GeoFEA, it should give you the same answer as the associated flow. They should be the same. Okay? So this is how it basically worked out. Now, okay, the question is, now we have noticed this, then how does it affect the stress-strain behavior of the soil after it has yielded? After it has yielded. Now, the critical thing is actually the undrained behavior. Okay? Now, if the soil is allowed to expand, if the soil specimen, you have a triaxial specimen, is allowed to expand, then all it will do is to keep expanding. So your volumetric strain will be very, very large negative number. Very large negative number. That's basically what will happen. But in the undrained analysis, the question will be asked, hey, in the undrained situation, there's no volumetric change. So what happened to this volumetric strain? Because the guy is trying to expand, right? But on the other hand, we say, sorry, you can't expand. And then what happened? This is how we work it out, how it is done in mathematics. In an undrained test, the volumetric change cannot occur. So therefore, we can say that the change in the incremental volumetric change equals to 0. Now, the situation is this. The total volumetric change has two components. There is an elastic volumetric change and a plastic volumetric change. Okay? The total volumetric change is the sum of the elastic and the plastic. The elastic and the plastic is the added together is the total volumetric change. What we have said is the total volumetric change, volumetric strain increment is 0. But there is plastic volumetric strain. You understand what I mean? There is plastic volumetric strain. So what does that mean? That means that the elastic volumetric strain increment must counterbalance the plastic volumetric strain increment. In the sense that the two added up has got to be 0. Alright? Now, what does that mean? If your plastic volumetric strain is negative, as in our case, it is negative because it's dilating. So what will happen to the elastic volumetric strain? It has to be positive. It has to be a positive quantity. So what it means is that you have to have elastic compression. Elastic compression. Okay? The elastic compression. So the soil is trying to dilate. Physically, it means the soil is trying to dilate, but the water is pulling it back in. So you develop suction. And what does that mean? Negative excess pore water pressure. So the negative excess pore water pressure is the mechanism of the soil to keep that volumetric strain the same or at 0. You understand what I mean? Okay? So the soil developed the suction to enforce elastic compression so that at the end of the day, the volumetric strain, total volumetric strain increment comes to 0. You understand? To balance out the plastic volumetric strain. Okay. So what does that mean? So mathematically, it means that the elastic volumetric strain increment must be the negative of the plastic volumetric strain increment. And since we know the expression for the plastic volumetric strain increment, which is this thing, alright, therefore, the elastic volumetric strain increment is just simply the negative of that, which is now positive. So you have now positive elastic volumetric compression. Is this volumetric compression? Alright, because it's positive. So now, what it means is that the soil skeleton is compressing. Soil skeleton is compressing. Okay? And we know from our Hooke's law, generalized Hooke's law, that the ratio as you compress the soil, the elastic volumetric strain occurs. As you compress the soil elastically, the mean effective stress has to increase. You have to increase the mean effective stress to compress the soil, right? And what is the rate of increase? Very simple. The rate of increase of mean effective stress with elastic volumetric strain is given by the effective bulk modulus of the soil skeleton. The bulk modulus of the soil skeleton. Now, so when you work that out, you realize that this is positive. So now we just cross this over to the right hand side. Okay, cross multiply to the right hand side. You immediately have delta P dash equals to K dash, which is the bulk modulus, effective bulk modulus, multiplied by the elastic volumetric strain. But the elastic volumetric strain is equals to this term, so you then substitute that in. And then, because K dash is equals to E over 3 into 1 minus 2 nu dash. Alright, so this is what happens. So, if you look at this, what this means is this. Your P dash is continuously increasing as the shear strain increases. Plastic shear strain increases. So, the mean effective stress is continually increasing. Continually increasing. So, if you look at it, so if the mean effective stress is continually increasing, what would happen to the deviator stress? Well, the sample is yielding. As we mentioned just now, if the sample is yielding, it cannot go outside into here. It can only go along here. Alright? So now if P dash is increasing, how would the stress path go? It can only run along here. That is the reason why yesterday when you run the thing, first you see a straight line coming up and then you just go up. That is the stress path. You see? Because you are forcing the stress path to go up there. Because the guy is trying to dilate. You're trying to force it back. The only way to do it is to increase the mean effective stress to recompress the soil skeleton back. Alright? And in doing so, what happened? The deviator stress that the sample can take is going to increase because of the linear relationship between Q and P on the U envelope. Alright? So essentially, this is what happened. So Q is going to increase at a proportion equals to M times P dash, delta P dash. Alright? So the rate of increase of Q will be M times the rate of increase of delta P dash, of P dash. And then when you substitute this thing equals to this into here, this is the rate of increase in deviator stress with plastic shear strain increment. And in a sense, you can write this out as this whole group of term as H, where you can say H is some form of plastic modulus. That is the slope, the gradient of the stress strain curve after yielding. After yielding. Not before yielding. Before yielding is obviously related to the Hooke's law. Right? But after yielding, so that's why some of you might have plotted the stress strain curve, and you find that in this kind of situation, actually, the stress strain curve just keep going up. It just keeps going up. It never level off. It just keeps going up. Okay? So that is the disadvantage. And what it means is that in effect, the soil never fails. Because you never reach a terminal strength. It just keeps going up. Okay? So this is essentially what is happening. And so when you plot the stress strain, I don't know whether I plot it here. The stress strain curve will look like that. I think when you run your FEM, you will see the stress strain curve looking something like that. Okay? Now, it doesn't mean that you cannot do something like that. It's just that when you do something like that, you have to be sure that when you run your FEM, the strain of the soil does not exceed the level where you are, which is valid. Okay, later on I'll illustrate to you to show what I mean. Because if you allow the stress to grow, to keep increasing to a very high level, obviously your prediction will be unrealistic. But it may be that within a certain limited range, your prediction is okay. It's okay. You know? So it depends on how you used it. There may be certain material that dilates very strongly over a short range. That is fine, as long as you don't exceed the strain level where the dilation starts to drop. Is that okay? So I hope this kind of answer, at least in some way, your question you have in mind, because the next part we are going into non-associated flow, and you will see the same thing again, but in a more generalized way. Okay? Now, in the angle of dilation, I won't go into the historical detail about the angle of dilation and who defined. It's all in your book, not in the book, in the notes. Okay? We'll talk about Bolton and then Tatswaka and all the rest of it. But essentially, to cut the long, No, when I give you the angle of dilation, it immediately means not associated. Because if you look at my angle of dilation, it's not equal to the angle of friction. Yeah. I have 3 angle of dilation, 5, I think 2 and 0. Right? And the angle of friction is 24. In no case is the angle of dilation equal to the angle of friction. So obviously it's non-associated. Okay? No. It will be like that, but not to a different degree. So I'm going to solve the thing and show you what it looks like. Okay? But the general form is actually quite easy to solve. I'll show you, in fact, the next few slides, we'll be discussing this. So, essentially, if you have an angle of dilation, just now I give you the definition. This is the definition of the angle of dilation. We can define, this is plastic. Plastic volumetric strain increment over plastic shear strain increment equals to minus 6 sine xi over 3 minus sine xi. We call this term N. Let's just call it N. Okay? Let's just call it N. Okay? Now, how do you visualize the plastic potential in this particular situation where you have a generalized angle of dilation called xi? How do you visualize this scenario? Okay, the way you can visualize it is this, that there exists, you look at the blue lines, there exists a family of plastic potential shown by the blue lines here, infinite number of blue lines, infinite number of plastic potential. Alright, and they are all inclined at a gradient of n, where n equals to this. Alright, n equals to this. Okay, 6 sine xi over 3 minus sine xi. So, basically, if xi is equals to 0, this set of line will be completely horizontal. If n is equals to the angle of friction, all this line will be parallel to the u locus. Correct or not? Okay? Now, you just imagine in the situation where all these lines are parallel to the u locus, you really only need one line, and that is the line lying on the u locus to completely define the flow rule. The reason is because the soil state will only be lying along the u locus. You don't need anything. If this family of lines is not on the is not parallel to the u locus, like in this particular case, how do you deal with it? Basically, the idea is that if you are on this point, you use this line and you take a strain increment vector that is perpendicular to this blue line. If you are at this point, you take a strain increment vector perpendicular to this blue line. But these two blue lines are in fact parallel. So therefore, the strain increment vector will be parallel as well. They will have the same inclination. You follow? They will have exactly the same inclination. If you are at this point, you will take a line going through this point, but that is parallel to these two lines. If you are at this point, you take a line that is parallel to this. So, in the case where you have the angle of dilation not equal to the angle of friction, which is to say non-associated, you have to think of it as an infinite number of lines intersecting the u locus. But where it is associated, you really need only one line because all the other lines are not needed. It will never, the stress point will never reach it. Correct? It will never reach it, so it's totally irrelevant. So only one line is relevant. But in this more general case, you have to think of an infinite number of lines cutting the u locus. Yeah. Practically, in most soil, I have not come across. Okay, I would say that in the short term, okay, the dilation angle, you're talking about real soil, right? Real soil, the dilation angle is not constant anyway. Because at the start, just after yielding a lot of very heavily over consolidated soil, will show very large dilation, but after a while it will just tail off. So in fact, you think about this, the dilation angle is very high at the beginning, at the end it is zero. So the dilation angle is actually a changing quantity. But the Mohr-Coulomb model is configured in such a way that it's a constant quantity. So that's the reason why the Mohr-Coulomb, you got to balance quite a few things to get it to work. You know what I mean? You got to balance quite a few things. It's an imperfect model. But then I can also tell you that all models in the world are imperfect. They are all approximation. No model can give you a complete and perfect description of soil behavior. A model like that will probably require a few thousand parameters, which is totally unrealistic anyway. So as engineers, we have to live with that. And so the art of the skill of the engineer lies in how he balances all these conflicting demands to come up to not a perfect solution, but a reasonable solution. Okay. So the angle of dilation can be quite high at the beginning, maybe something like, I have seen angle of dilation 10 degree, 15 degree, not quite as high as the angle of friction, but still fairly high. So, but it invariably it will go to zero. That's why there is a problem with the Mohr-Coulomb in that sense. But you can't stop people from using the Mohr-Coulomb because, like Prof. Junaida said, I don't have the data. I don't have property, parameter. How do I use anything more complicated? It's impossible. Sometimes even Mohr-Coulomb is pushing it. So basically, this is the situation. So basically, in actual fact, but of course you can say, now I can come up with if you can come up with a soil model where the angle of dilation is a function of strain or something like that, and you can prescribe or develop a model that is self-consistent in that sense, perhaps you may create a software that is very marketable. A lot of engineers want to use it because this is simple enough, and you have to assume a rate of decrease for them, probably, because engineers don't like to have too many variables. If you have too many variables, they can't get the hang of it. They don't know how to prescribe. I mean, that's the reason why Plexis is so popular, because everything is assumed. All right. So a lot of people, the danger, of course, is that you can be assuming the wrong thing for them. Okay. So anyway, that is a small digression from here. Usually, the angle of dilation is less than the angle of friction. So this is more the general scenario where the gradient of these blue lines are actually more gentle than this black line. More gentle than the black line. And they tend to intersect this way. Alright? The minimum gradient is a flat horizontal line. Usually you don't have a family of plastic potential that go like that in Mohr-Coulomb. And a lot of programs will not allow you to specify that, because that would imply negative angle of dilation. Is that alright? Okay. So basically, and in fact, is the slope of the family of plastic potential. So in fact, when you look at Xi here, this thing here, this angle of dilation here, it actually determines the slope, the gradient of the family of plastic potential. And when Xi equals to the angle of friction, alright, the slope of this, the gradient of this line is equals to the gradient of this line, and that is associated flow. Clear? Yeah. That part is purely elastic because you haven't hit the U locus. Correct. But you haven't yielded. So the plastic potential is not activated. No, the plastic potential is only activated when you are on the U surface, on the U locus. Because you have not yielded. You remember the blue bar and the red bar I showed yesterday? Until you reach yielding, only the green bar is activated. Only elastic behavior. So, even though the line has crossed the family of plastic potential, there's no plastic behavior. There's no plastic behavior over here. So that part is irrelevant. Only when you hit the U stress, then the plastic behavior is activated. At that point, it looks for the family of plastic potential. You got an idea? Okay. So this is how it worked out. Okay. So I hope it gives you some very detailed idea of how that model actually works. Okay. Now, the question is, okay, if I have an angle of dilation that is not equal to the angle of friction, then how do I calculate the rate of increase? In fact, there is an analytical solution. That's why I say I'm giving you the solution to your assignment here. So you don't have to do much. If you just check, make sure it's there, okay, hand up. Alright, give the explanation, type it in and then, or write it in and hand up. Okay. So basically, right, the question is, alright, what would happen if the angle of dilation is not equal to the angle of friction? In fact, the situation is similar and we can do a similar set of calculation. We can now examine, okay, this one is actually all there. In fact, already explained this already. What would happen if the angle of dilation is not equal to the angle of friction? What would happen to the stress strain curve and the stress path? Alright. Basically what will happen is that you still have this relationship, delta epsilon Vp, the incremental plastic volumetric strain is equals to minus, instead of m now, is n. Alright. Because of this relationship. Alright. So the plastic volumetric strain increment is equals to minus n times the plastic shear strain increment, where n is equals to this. Okay. So we apply that, we actually go through the same procedure again. And we say there's no total volumetric strain increment, only plastic volumetric strain increment. So therefore the elastic volumetric strain increment must counteract the plastic volumetric strain. And you apply the same condition again. This is exactly the same condition, which leads you to the conclusion that the elastic volumetric strain increment must be the negative of the plastic volumetric strain increment, so that they two add up to be 0. Alright. And since the plastic volumetric strain increment is minus n times the plastic shear strain increment, this just simply becomes the positive of the plastic shear strain increment. And then you apply the same relationship again. Delta P dash over the elastic volumetric strain increment equals to, divided by that is equals to the bulk modulus, the effective bulk modulus. You will then get this thing now, and if you look at this expression, you compare this expression with the previous expression that we have. The only difference is instead of m, you get n. You understand? Instead of the m there, here, you now have the n. That's all. And so you go through the same thing again. The rate of change of deviator stress is equals to m times the rate of change of mean effective stress, which is actually the equation of the U locus, the gradient of the U locus. And immediately you come up with this. And when you compare this term with the previous term, you realize that in the previous term it's m squared, but now it's m times n. That's all. That's different. So instead of m squared, as in here, all I have is m times n, which is here. You see? So if n is 0, then what would happen to the stress strain curve? If n is 0, if the dilation angle is 0, angle of dilation is 0, then what would happen to Q? Q will just flatten out. There's no delta Q. Delta Q will be 0. So the moment you yield, the line will just go horizontal. Now that is more like the elastic perfectly plastic kind of situation. That is why programs like Plexis by default will give you a 0 angle of dilation, because that is the most conservative. In most cases, it is the most conservative. Is that okay? It is the most conservative. So if you have a positive value of n, positive angle of dilation, it will lead you to a positive value of n. A positive value of n will give you some increment in deviator stress, so that your stress strain curve is going to look like that. In fact, this is part of the solution. This is for high angle of dilation. I think it's 5 degrees. Oh, in fact, this is a solution. 5 degrees. This is 3 degrees, not exactly the solution, but that's 2 degrees. And then if you have 0 degree, it should go like that. So when you run it, just make sure you get something like that. Is that alright? Just make sure you get something like that. Now, this is a curve from the particular soil that I show you, where there are 3 stress paths, 3 set. This is one particular stress strain relationship. And you can see that if you are using 2 degree angle of dilation, your solution will be conservative up to about 8% shear strain. 8% shear strain. If you are using 5 degree angle of dilation, then your solution is only conservative below the actual stress strain curve up to about 2.5% shear strain, 2.5% shear strain. So, if you want to push the limit, I mean, of course you start by using 0 angle of dilation, and sometimes you use 0 angle of dilation, the ground movement too large. Then, and you are employed by a contractor, and the contractor will say, hey, come, try to push it a bit, push it a bit. You know, I'm sure contractors do this kind of thing. In Singapore, they all do. Push it a bit, push it a bit. And so how do you convince the client and how do you convince the authority that you can use a positive angle of dilation? So you try a positive angle of dilation, and what you can do is you can use a small positive angle of dilation, then your line will go tilt up slightly. But just make sure after you finish, check the shear strain throughout, the shear strain contour in your result, and make sure that at least in most of the places the shear strain doesn't exceed the intersection value. That will be how you can, one way you can actually deal with the situation. So at least you can go up to the client and say, yes, I'm using a non-zero angle of dilation, alright, but you can see in principle all my predictions should be still conservative. Alright, if you are using a zero angle of dilation for this soil, it will be forever conservative. So the question is, how conservative or non-conservative you want to make your solution? You can kind of tune it by changing the angle of dilation slightly. You get what I mean? Compared to the real stress strain curve. So this is one way you can play with the situation. But of course, the first thing you want to do is to say, okay, I start with the most conservative and I see whether it works. If it works, then I don't have to worry. But if it doesn't work, then if I want to earn the contractor's money, then I see how I can work out a case that will allow me to, in a sense, I won't say it's not quite like a lawyer. A lawyer will argue until black becomes white. You're not going to do like that. You're going to still stay conservative, but just to give a more optimal, slightly more optimal solution. I mean, this is the art of being an engineer, right? After all. Now, there are also people who I have come across who did the, I don't know how to say it, who just used angle of dilation equals to angle of friction, but I just don't declare it. There are people who does that. And you know what? Sometimes authority they are not smart enough. They don't understand all this theory. You know, authorities, most of the time the engineers working there, they go through checklists, they don't understand all this thing. And so they never think of checking the angle of dilation. Alright? So I have come across people in Singapore who get through like this, using associated flow, which I would never recommend, but somehow they got through. So obviously somewhere along the line, someone never checked. You know, and it's not a common thing to check angle of dilation. You got to understand things before you can check angle of dilation. So if you are on the regulatory body side, you will ask, what is your angle of dilation? You know what I mean? You will be smart enough to say, hey, what do you use for the angle of dilation? So that is one question you can ask if you are working on the other side of the fence. You know? Okay, so this is basically what it is. Okay, now in terms of the stress path, how does the stress path looks like? If you look at the stress path basically says, if you look at Q, alright, Q is still equals to M dQ, delta Q is equal to M times delta P dash. So the stress path will still move along the U locus. That's the only way it can move. There's no other way it can move. Basically, Q will increase. But what is the rate of increase in Q? It will be guided by the U locus. It will be. It cannot move out to here. It cannot move out to here. So it will be guided by the U locus. It will only move up. But what is the rate of movement? Where is the difference between different angle of dilation? The effect of different angle of dilation is that the stress point will move up this line at different rate, at different velocities. And they will reach different endpoints. Why? Because the rate at which they increase with plastic shear strain increment is dependent on N. If N is 0, that stress point will just stay right there. If N is very large, it will shoot up very far. If N is intermediate, it will go intermediate. You get what I mean? So this is how it works out. So I think many of you got this thing, you saw this yesterday, and you were puzzled probably why it looks like that. This is why it looks like that. Okay? Now, the question then is, what happens if it is a drain situation? If it is a drain situation, what would happen? This is another question in your assignment. Basically, if you look at it, an undrained stress path, right? What happened to the drain stress path? The undrained stress path in an elastic material is always vertical, right? Now, when it hits yielding, then it starts to go all over the shop. Okay, it starts to go all over the shop. And you can see the stress path following the U locus. And when you look at this is not totally unrealistic because in an undrained situation, I show you the other stress. You can see the stress path following the U, roughly following the U locus, but some parts did exceed it a little bit, but in general it tried to follow the U locus. Okay, so this is roughly what happens if it is undrained. The question is, what happens if it is drained? Now, if it is drained, what would the stress path look like in a triaxial test? In a triaxial test, the stress path will look like the total stress path. Alright? And you remember the total stress path is a straight line with a gradient of 3. So the total stress path will just, the stress path will just go up with a gradient of 3 until it reaches here. Now, the problem with the drain test is that the stress path, the effective stress path is determined by you, because you control the pore water pressure. So you control the total stress, you control the pore water pressure, so effectively you control the effective stress path as well. So the effective stress path is completely dictated by you. Completely dictated by you. So the effective stress path will just go up to here, and then what happens? It will try to overshoot this because it's still 3 to 1, a gradient of 3. It will try to overshoot, but it cannot overshoot because the soil doesn't allow it to overshoot. And so therefore it will just stay here. Alright? And what it means is that when you look at the stress strain curve, the stress strain curve is just like an elastic, perfectly plastic. Just go straight line and then flat out. No more increase in Q. No more increase in deviator stress. No more increase in deviator stress. It will reach the plateau and it will just stay there for a drain test. That's why people are not so concerned with the drain test. Not so concerned with the drain test. Drain situation, because the angle of dilation in the drain situation is not so direct. In the undrained situation, it directly affects the stress strain curve. You get what I mean? No? It directly affects the stress strain curve. Now, that I think in a sense sum up the solution of A and B. I don't want to tell you that. I mean, when you look at it, you'll see that it's pretty much there already, all there. So you just kind of put everything together and, and just fill in the solution. All right, what you generate on the screen, some screenshot and some explanation, we're all done. Okay, so I think I expect everybody to do very well. All right, okay, yeah. Horizontal, yeah, yeah. It's like that. It basically looks like that. It just looks like a. It just looks like that. If that's what you mean, that's what you mean, right? Yeah. So what you think of it this way: if you have a very large dilation angle, this slope, this gradient will be very large. A smaller dilation angle will be like that, and then in the limit when you reach 0, it will be like that. So as you reduce the dilation angle, the whole thing should come down. Cannot be modeled. That's why Mohr-Coulomb cannot model it. Because to model it, you actually saying that the angle of dilation is negative, which cannot be prescribed in Mohr-Coulomb. So therefore, they will not allow you to do that. So that is the reason why. I mean, this is all related in a sense related to the method A, method B, because the Mohr-Coulomb cannot prescribe compression. And the stress path going to the left implies you are generating positive excess pore pressure. And that can only occur if the soil is compressing. And so it all ties in together. You cannot do that with the that's the limitation. So as a modeler, you need to understand the limitation of the Mohr-Coulomb. And I think it is very important that people understand the limitation and how the Mohr-Coulomb operates in a very intimate way, because this is likely to be 99% of your time, if you go into practice, this will be the model you will use, whether you like it or not. Unless you are very, very gung-ho and you want to go and write your own model, and even then you have a problem convincing your client that your model is good, is okay for the soil. You know what I mean? Yeah. Now coming up to the last bit on angle of dilation. Basically, as I mentioned to you, the angle of dilation is not a constant. So far, everything that has been done indicate that the angle of dilation is changing. And the thing that people have always investigated is not angle of dilation, but is the maximum angle of dilation. The maximum. Alright? the maximum angle of dilation. And one of the classic paper is by Bolton, 1986 in Geotechnical. It's called Strength and Dilatancy of Sand. And that paper I strongly advise you to read, because whether you use it or not, this is the paper that has been cited close to 1,000 times over the years. So it's very, very classic. Very, very classic. And I was very fortunate when I was in Cambridge. Malcolm actually presented a seminar on his paper. So I came to know this paper quite early in the day. Back in 83 or 84, he already presented a seminar. So anyway, he proposed an empirical relation, okay, which is that the peak angle of friction minus the critical state angle of friction is equal to 0.8 times the maximum angle of dilation. Maximum angle of dilation. So you can use that if you want to estimate the maximum angle of dilation. But I would say that in fact the maximum angle of dilation is not directly applicable to you, because you want an average angle of dilation. You don't want a maximum. If you model after the maximum, then you're definitely unconservative. Correct? You're definitely unconservative. So that essentially is what there. And then there are other people since then. Shens and Vermeer, basically 1996, also proposed angle. I think this is a technical note in Geotechnical. Okay, so basically the main thing is that the peak angle of dilation is not a constant. Angle of dilation is itself not a constant. It will start off at a reasonably high value, but will fade away to zero near to the critical state. All right, and there are some software. I think Abacus is one of the software. I think GeoFEA is okay. GeoFEA will take zero angle of dilation, but Abacus, for some reason, you got to give it a very small positive angle of dilation, like 0.1 degree. Otherwise, that was a version of Abacus I used at 6.7. Otherwise, it just go unstable. Okay, so you have to explore the software a bit. Okay, right. I think that's basically it for the angle of dilation. And I've already mentioned this to you, how you can tune the stress strain curve using the angle of dilation, and use that stress strain curve to compare with the actual measured stress strain curve to, in a sense, choose a more optimal value that will still meet your client's performance criteria and still be conservative. Okay? Sorry? Yeah, the dilatancy index, yeah. Okay, the dilatancy index is nothing more than an empirical thing that was defined by Bolton, and it is related to the angle of I can't remember what is this dilatancy index, but it's an empirical index defined by him. Basically, that relates the peak angle of friction to the critical state angle of friction and the dilation. So basically, this is something. It seems that a lot of people does define this. But I don't think you need to go through, if your purpose is to get an angle of dilation, you should not need to use the dilatancy index. Because the thing that is more obvious to you will be the peak angle of friction and the ultimate angle of friction, because that's what your triaxial test will directly give you. So if you can relate that to the angle of dilation, okay, I think that is sufficient for using the Mohr-Coulomb. And this is really what it is. This is really the kind of thing that you need. You see, but in some cases, if you are using Malcolm Bolton's case, then you may want to say, okay, for triaxial condition, this is equals to 3R, and I then derive the value of 3IR, the dilatancy index, and then I plug into Shens and Vermeer as an alternative relationship. I then get the maximum angle of dilation. Now that is an intermediary. Is it really an intermediary index? It's an intermediary index. You don't really specify that in the software, and you don't really measure that. Yeah. For the software, dilation angle. No, that's why I say that even this in itself, the maximum angle of dilation is not directly applicable. If you specify your angle of dilation equals to the maximum angle of dilation, immediately you're unconservative, because everything else is going to be lower than the angle of dilation. So I would say that the maximum angle of dilation is useful only as a guide to how high you can choose it, the upper limit. But you usually will not use the upper limit. You will use maybe 50% or 30% or 20% of the upper limit. That is how because you want to factor for the fact that as your strain increase, your angle of dilation will go below the peak. So the peak is only useful as an upper limit. So if your peak tells you that your peak angle of dilation is 10 degree, you evidently cannot use associated flow rule. That's completely out of the question. You know what I mean? And even using 10 degree is too much. In fact, a lot of people these days, I was talking to David Hyde several years back, and I asked him, what is the practice? And the practice is now using lower and lower angle of dilation. In that time, in those days when I was talking to him, 2008, 2009, he was saying that in the UK, they were using something like 4 degrees or 5 degrees. And on hindsight, I thought that was rather high. I mean, honestly speaking, I thought that was rather high. If you ask me now, I would use like 0.5 degree or 1 degree. You know. Because when you look at the stress strain curve, the 5 degree will, actually the gradient is pretty high, you know. It's pretty high, it's not low. Post-yielding is still very high. You can look at this thing. That's 5 degree, the top curve. And it's very high. I mean, as an engineer, you're saying that this thing is only conservative up to a strain level of 2.5%. Are you comfortable with that? You know, I would be more comfortable with something like 10% strain, you know. Is that alright? So you ask me, I'll say, I'll probably use 1 degree angle of dilation. You know, but then if somebody really twist my arm, I may go up to 2 degree and I'll say, okay, let's try it and see how it looks like. But this is really how, as an engineer, you have to be careful when you push the boundary. You have to be careful. I mean, there's no hard and fast rule, you know. So you have to keep checking with if you have a set of stress strain curve data from a triaxial test that looks like that, I would suggest that you keep checking with it and make sure that at least you are not unconservative with respect to it. You know, but I would say that it doesn't mean that if you exceed it, you will definitely collapse, because most of the time the triaxial test stress strain curve is conservative because most of the test specimens are disturbed in some way. And so as a result, the actual stress strain curve is probably well below the measured stress strain curve is well below the actual stress strain curve. So there is some, but you don't know how much is the factor of safety. That's the thing. You know, yeah, sort of like going towards a waterfall, but you don't know how far you are from it. That's the danger. That's the danger thing. Yes. Are you referring to this point? This point here? Oh, that is that point and this point, you mean? This point. Okay. How do I get this point, you mean? How do I get it? Okay. This is the U point that I deduce from the stress path. Okay, I'll show you the stress path. Now, remember I told you the stress path. I take this, actually I use the stress strain curve corresponding to this sample. Alright. And you can see the stress strain curve tells you that at a Q of about 110 kilopascal, S of about 100, T of about 110 kilopascal, the thing turn over. So if that is the radius of the Mohr circle at which the yielding takes place, the turning around point, the point where it turns around, I take it to be the yielding, because it suddenly, from a nicely elastic stress path, it switches over to a plastic stress path. At that point, I take it to be the yielding U point. So when you look at the U point, this is the T value, which is the radius of the Mohr circle, is 110. So for the Q is twice that. Alright, the Q is twice that. So when you look at the Q I use 200 something. It's actually 2 times that particular value. So I used that. I didn't use this particular point for the stress strain curve. Now, I'm not saying that this point is wrong. It's just that I usually find that if you use the stress strain curve, it is very hard to define where the yielding occurs, because the curve around in quite a gentle way. So you could be using a point here, here. It could be there. So there may be some argument as to but if you use the stress path, you tend to be quite sharp. That turnaround point tends to be quite sharp. Now, I'm not saying that you are wrong in doing it. You can do that. So you can use this point over here. But if you use this point over here, I would suggest what you do is you choose a Young's modulus that is representative from here to here. Now I'm able to choose a Young's modulus that's very high because I'm taking this to be the U point, and so I just take the secant modulus here. Now, if you take this to be the U point, then you cannot use this as the Young's modulus, because then you'll shoot the curve right up to here, the elastic portion, which is wrong. If you want to take this to be the U point, you want to say my elastic portion is down here, which is conservative. You know what I mean? And so your Young's modulus will actually correspondingly drop. So it's not necessarily more optimal. Not necessarily more optimal. Okay? But ultimately, which one will save you money? There's something you have to try. Okay? So essentially, you can use this point as the U point. There's no harm. It's basically there's no hard and fast rule to say how you should choose the U point. But if you use this as a U point, you can. Then you have to use this secant modulus from here to here. And then, obviously, you cannot use much of an angle of dilation. If I were you, I'll just use 0 angle of dilation and just go through. Because really, there's not much headroom for you to work with. You know. Okay? So, basically, you choose a higher U point, you get a longer elastic range, but your Young's modulus may drop, your angle of dilation may drop. So, which one will save you the most money? I don't know. It's something you have to, when you run it, you will know. That depends on the problem. Is that okay? Okay, so I have finished with that. Now, the yielding of real soil. Now, the basic problem with the Mohr-Coulomb is that when there has been a lot of research and testing on the U envelope of real soil, and what we found is that the U envelope of real soil typically looks something like that. I mean, this little kink here is unintentional because I was using the drawing facility in Word and it doesn't come out. But essentially, there are there's 3 different regimes. Regime number 1, okay, regime number 2, and regime number 3. Okay, regime number 1 prescribes the behavior of the soil under very, very low effective stress. And this regime, unfortunately, is actually still not well investigated. That's my point. My thinking is not well investigated. And in fact, there's a limit. If you use triaxial test, there's a limit to how far you can explore. It's something that you may want to bear in mind if you are using a triaxial test in research. Okay, there's a limit to how far to the left you can explore the particular thing because the stress path will refuse to go beyond that. Okay, I'll explain to you. This is roughly what happened. If you have a triaxial test specimen, if you look at it, how many of you are doing triaxial tests or have done triaxial tests? Okay. Now, if you do very, very low effective stress, okay, what happened is this. At very low effective stress, if you look at your triaxial test specimen, this is the end cap, this is the specimen, that is the bottom platen, and then you got a rubber membrane that comes down like that. Right? Okay? Now, if you look at this, supposing you have a total, a cell pressure, sigma R, total stress, acting on the outside, alright, and you have effective stress. You have a certain level of effective stress, but you also have some pore water pressure on the inside. Okay? Now you look at the equilibrium of this rubber membrane. It's very interesting because obviously you do not glue the rubber membrane onto the sample. You obviously don't do that. So therefore, supposing what happened is this, supposing your excess pore water pressure or your pore water pressure at any point of time exceed the cell pressure. If U is greater than sigma R, what would happen to the whole thing? This whole thing, the pressure, the contact pressure between the rubber membrane and the soils will tend to be negative, which cannot happen. So at the point when the contact stress, when U equals to R, the contact stress goes to 0. And when the contact stress goes to 0, the rubber membrane detaches from the soil. The soil may still hold together, but the rubber membrane will detach from the soil. And when the rubber membrane detaches from the soil, what will happen? The water will start flowing out. So you immediately lose your undrained condition. So you cannot prescribe undrained condition up to a point when U is beyond U equals to R. But when U equals to R, then you know that sigma R dash equals to sigma R minus U equals to 0. So therefore, the minimum sigma R dash effective radial stress you can impose on the sample is 0. Alright? Sigma R dash equals to 0. Now, let us think about this. What will happen? Where is the boundary if sigma R dash equals to 0? We know that Q equals to sigma A dash minus sigma R dash. Correct? If sigma R dash equals to 0, this is equals to sigma A dash. Agree? Okay? P dash equals to 1/3 of sigma A dash plus 2 sigma R dash. Right? Now this is equals to 0. This is 1/3 of sigma A dash. So what is Q over P dash? Q over P dash or Q over P dash is equals to 3. Or Q equals to 3P dash. So therefore, there is an imaginary line, okay, passing through the origin here with a gradient of 3 to 1 that your triaxial test sample will not go beyond. It will not go beyond. You're unable to bring it beyond. That is the limitation of the triaxial test. And we actually mentioned this in the 2014 paper in Soil and Foundation, Xiao et al. Because this is the limitation of the triaxial test. Because the rubber membrane will automatically detach unless you are able to glue it. But I don't see anyone gluing rubber membrane on the soil. So that definitely is out of the question. Okay? So this portion is not well explored. Now, the most well explored portion is actually regime number 2, which is more the Mohr-Coulomb kind of regime, where you have a straight line going up, and that is the kind of regime number 2. And this is where the Mohr-Coulomb model works very well. It works very well. There is a third regime, which is actually what I personally call a compression cap, which basically allows the soil to undergo volumetric yielding. And this is important for soft soil. Very important for soft soil. And this is the shortcoming of the Mohr-Coulomb, which is related to the method A that we have seen before, and which is also related to the fact that the Mohr-Coulomb is unable to model compression. So this is essentially all related. So when we go on to the next part, starting tomorrow morning, I will be talking about critical state soil mechanics, leading you into chem clay as a basic example of how a model with a compression cap can be defined. Okay, so that hopefully will allow you then to see, oh yeah, this is how these models, current models typically, and I'm not saying that the chem clay is perfect. Chem clay is not perfect. It's actually far from perfect. But it is able to, it is able to cover up some of the Mohr-Coulomb's principal weakness. And that is worth us looking at it. Is that okay? I think that brings us to the end of the Mohr-Coulomb. Is there any question that you would like to ask me? Oh, okay. Limitation of triaxial test. I examine a small region, say a region here. The contact between the rubber membrane and the soil surface. The contact between the rubber membrane and the soil. If you look at the equilibrium equation of the rubber membrane, on one side of the rubber membrane you have the cell pressure acting. On the other side you have the pore pressure acting. Assuming that your rubber membrane has no stiffness at all. Alright, just a membrane with no stiffness. Then the membrane will be pressed against the soil as long as sigma R is greater than U. Alright, the moment U is equals to sigma R, that contact stress goes to 0. And what happens? Pore fluid will come out and push the membrane outwards. There's nothing to stop the pore fluid from coming out. You can only stop the membrane is only good for stopping the pore fluid going in. But pore fluid will only go in if this guy is bigger than this guy. If this guy is bigger than this guy, pore fluid will go out. And what happens? It will push the rubber membrane out. So the whole rubber membrane will detach and you have a pocket of water between the rubber membrane and the soil. And immediately you lose the undrained condition. The sample becomes a partially drained sample. You've got to keep your pore pressure below your confining pressure. Yes. In a sense, you've got to make sure that your lateral effective stress is not 0. Must be greater than 0. If your lateral effective stress is less than 0, you got a real problem. Because essentially for the soil, you can say that the lateral effective stress is equals to the lateral total stress minus the pore water pressure. So if these two are equal, then this guy goes to 0. So therefore the condition is that this guy should not be less than 0. Okay. So if you ever develop a condition where the soil sample is getting close to this, you'll find that all your stress path will not, in fact, it will naturally not go there. It will just go along that particular line. Basically, there's a particular line over here, P dash and Q. This is 3 to 1, where all the soil stress path will try to move along there once you reach it, because it just cannot go beyond there. That is the limitation of the triaxial test. Okay, and that is the reason why this portion here is cannot be explored with the triaxial test. Sorry? No, it's nothing to do with the plastic. It's the equilibrium of the rubber membrane. It's merely the equilibrium of the rubber, and nothing to do with the soil sample. You know what I mean? The rubber membrane just cannot hold it. Alright? So I hope this is useful to you, because I realize a lot of people are not aware of this thing. You know? And we were rather surprised when we saw the stress path all following that. And then we suddenly figured that, oh, it was because of the rubber membrane problem. Okay? So this region here, you cannot explore. It's out of bound. If you use a triaxial test, you cannot explore that region. So yesterday somebody asked me, if I have a model, how do I get the C here on the PQ space? No way. Because your triaxial test result cannot come through to here. So you can only approach it by theory and say, I fit a curve to this portion, I project it back, this is where it hit. You get what I mean? Okay. Now you actually have a similar limitation even if you plot it on the standard Mohr-Coulomb framework. On the standard Mohr-Coulomb framework. I can tell you where is the limitation. On the standard Mohr-Coulomb framework, the limitation occurs here. You know, this is the standard Mohr-Coulomb plot. Alright? And you might say, okay, there is actually a failure envelope here. And you draw the Mohr circle. Now, the limiting Mohr circle will be this. Something, basically what it means, the end point of this Mohr circle cannot go negative. That's the point. Because sigma r dash cannot go negative. So your Mohr circle cannot move this way. It can only reach this point. So there are some region over here you cannot explore. You get what I mean? You cannot explore with the Mohr circle. You got it? So basically, it doesn't mean the triaxial test can actually go all the way. It cannot. There's some certain region it cannot go. Any other questions? Extension test. If you are doing extension test, my sense is that the problem is not relevant to the extension test, but then in the extension test, you can only enforce extension. Usually the way you enforce extension is you press the sample together this way, right? So the idea of zero effective stress in the lateral direction should never occur, because you want to have a high lateral effective stress to squeeze the sample out like a toothpaste. Right? So in fact, you want a very high sigma r dash. The sigma r dash has to be higher than sigma a dash in order to get your sample. So in fact, your sigma r dash is the major principal stress, not the minor principal stress. You get what I mean? So that problem is irrelevant. Okay?